Okay, we'll take a quick look at the calendar. Today we are going to cover systems of equations using algebraic methods. Last time we graphed two lines and often they would intersect and we would grab that point of intersection. And today we're going to be looking for the same point of intersection, but we're not going to be relying on graphs. We're going to be doing this instead using algebra. Wednesday is our first day of applications, that is word problems of these systems. And then Friday is our second day of applications. Monday, a week from today, is our review for the exam. And then Wednesday next week is test number 1. Questions on the calendar? So Wednesday next week is our first test. Okay, so we'll begin here on page 70. And just like last section, I think I wrote way too much stuff in this packet that I gave you. So we're going to be jumping around and doing kind of a sparse version of what I've written up here. Let's just start at number 1. And who's ready? Victor? Can you read number 1? Thank you. Morgan, number 2. Okay, so let's take a moment to analyze this graph. So what's represented on the horizontal axis is minutes. So what are we measuring there? We're measuring time. And then what are we measuring in the on the vertical is the height. Okay, and so we've got 2 people here, Peter and Linda, both math teachers here at GCC. So what can we say about Peter looking at that line? He's descending. And how does his starting position compare to Linda's? So he starts off higher, like we can just physically see it here, and then he's descending. And then, and what can we say about Linda? So initially she starts lower, but what is she doing? She's ascending, she's getting higher and higher. And what do you think is going on right here at this point? They're at the same height, not necessarily in the same exact space, we hope not, but you know, they could be like just going right next to each other and at the same height at that one moment. So looking at this graph, let's just go ahead and write down the solution to the 2 equations. So what are the coordinates there? I think each of those is 200, is that right? I think that's good. And so that means 16 what? 16 minutes after noon. 2200 is what? The height of which one of them? Of both of them. That's the idea. So they're both at the same height at that exact moment in time, 2200 feet above the ground. Okay, so that's the solution. Now, this was an easy problem to solve because we had a really accurate graph in front of us. But we know that drawing this kind of picture takes a long time normally, and even when we draw it, it's still not 100% accurate. So what we're going to do is we're going to solve this kind of a thing without relying on the graph. So let's jump to the next page. Again, I said we're going to skip around a little bit. And here in number 4, you will see 2 equations. And I will tell you that the y with the little Peter next to it is Peter's height after x minutes. So y is the height and x is the number of minutes. How can we tell that Peter is descending looking at the equation? It's a negative in front of that slope, right? Negative 50. In fact, that negative 50 means something very specific. It's a slope. What does it mean? His height is decreasing at 50 feet per minute. And then what does the 3000 represent for Peter? That's the y-intercept where he started from. And Linda started at 600. Okay, that makes sense, lower. And she's increasing, that's a positive slope. And she's increasing at 100 feet per second. And so what we're going to do is we're going to solve the system of equations, just playing with the equations and not thinking about the graphs. So here's the basic idea. I'm going to cross off the word Peter and Linda temporarily. Usually you don't have them separated like that. They're just all y's. And I will say that if you think about the picture on the previous page, what's true about the y-coordinate for both Peter and Linda at that point of intersection? What's true about the y-coordinate for both of them at the point of intersection? They're at 2200. Pretend we don't know that. Pretend we just have this generic hazy picture and they're intersecting lines, but I can't tell it's exactly 2200. But what's definitely true about the y's for both people at that point? They're definitely the same. Even if we don't know it's 2200, I know that at a point of intersection, it's the same point. So it's the same y. It's the same x for that matter. So if it's the same y, then what I can do is I can say, well, instead of like this y right here, maybe I put this stuff because it's exactly the same y. Another way to say that is that we're going to take this value of y right here and we're going to substitute it into that y right there. So we're going to replace one y with the other y. So here's what we're going to do. I'm going to copy this equation right here, but I'm just going to copy the right-hand side. So there it is. And then instead of the left-hand side, well, it used to say y for Linda's height. But we know that if we're at the point of intersection, that's exactly the same as Peter's height. But Peter's height is given with this thing with x's. So I'm going to put that stuff right over here. Negative 50x plus 3000. So maybe I can actually clean this up a little bit with my arrows here and say that this stuff got copied right there. And then instead of y for Linda, we decided that we were going to write all of this and bring it down there, right? Because it was the same y for both. And that right there is an equation that we can solve. It has only x's in it. We've got x's on both sides, so let's bring all the x's to one side or the other. It doesn't matter. I generally try to keep my stuff positive if I can. Should we bring the x's left or right? Let's bring them to the right. So we'll add the 50x to both sides. And then we'll move that 600 over by subtracting. Last step, how do we solve for x? What do we do to both sides? Okay, 2400 over 150. Either reduce or type into your calculator. Somebody tell us what we get. 16. Which should sound familiar because that's what we saw from the picture. But the nice thing about this method is that it doesn't rely at all on having a picture or drawing a picture or any kind of accuracy of a picture. It's just playing with equations. And so it's like 100% accurate. Okay, this is a partial solution. This is the x value at the intersection, but it would also be really nice to give the y value at the intersection. So if I know that x equals 16, well, I can plug into either of these y equals equations to find the y value. And if I did this right, then whatever you get by plugging 16 into the one equation should be exactly the same as when you plug 16 into the other equation. So we'll just say plug x equals 16 into either equation. I'll plug it into Linda's equation. Let's see, so that says 100 times x plus 600. 100 times 16 plus 600. Okay, so that gives us, let's see, 1600 plus another 600, 2200. which should also sound familiar because that was the y coordinate at the intersection point. Any questions on what we just did? Okay, so let's run through the process real quick and then we'll do another example. What we did was we replaced the y for one equation with the y for the other equation, and that gave us a brand new equation which had only one variable in it, which is a lot better than having two equations with two variables. And then we did some work to solve for the one variable, and then you plug that variable into either equation to find the other. You're not done until you have both x and y. Okay, so let's try the same technique here on number 5. So here are our two random equations. And we're trying to find the point of intersection. So we have in our heads this fuzzy picture of two lines randomly floating around on graph paper. And we know that at the point of intersection, the x and the y are exactly the same. So we're going to use that fact and we're going to avoid graphing entirely. Now this is a little bit tougher because neither one of these equations is of the form a single letter equals, like y equals. So we got to do a tiny bit of work first to get this one in a better form. What we need to do is solve one of these equations for one letter. We have to solve one equation for one letter. That actually gives us 4 different choices, and we're going to pick one of these 4 things. Solve the first equation for x, or solve the first equation for y, or second equation for x, or second equation for y. Now sometimes some of those choices are harder than others, so I want to give you this one little clue to tell you how to pick the easiest choice if such a choice exists. I'm going to write this down, but don't copy it. If I solve this equation for x, for example, if I just pick that one of the 4 options, got to get x by itself, so first I move this negative 2y over by doing what? Adding it. So that gives me 6x equals negative 3 plus 2y. Add the 2y over. And then what do we have to do to solve for x? Divide by 6. And that makes me unhappy because that means I have fractions. And I'm not opposed to fractions from a philosophical standpoint, but just if I can avoid them, I'd like to. So there you go, you've solved for x, and it is perfectly legal to do what we did. And the next step, which we are not going to do, would be to replace this x right here with all of this stuff, because that x is exactly the same as this x. But it's messy because it's got a fraction in it. So instead of doing that, we're going to make a better choice. So solving the first equation for x led to divide by 6, which was fractions. What if you had to solve this equation for y? What would your last step be? Divide by negative 2. It's fractions, right? What if you solve this equation here for x? What's the last step? Divide by 4. It's fractions. What if you solve this equation for y? No fractions. This is the one that's easy. What makes this easy is the invisible 1 that's right there. So that's the choice I'm going to make. Sometimes all 4 of them lead to fractions and there's no way of avoiding it. But if I can avoid it, you better believe I will. So let's solve this guy for y. So we'll move that 4x out of the way by subtracting it. No fractions. And then here's the key idea. We're going to take the y in one of the other equations and substitute. Replace the y up there with the stuff we just found is equal to y. So there are 2 different y's that we might substitute. And I will tell you that one of them will just get you going around in circles and the other one will advance you towards the solution. What you need to do is substitute into the equation you didn't use. Which equation did we use to get this blue y equals, first or second? we use the second equation. Don't plug into the second equation. Plug into the other equation. So we'll write that. Yeah, I'll show you what happens if you plug into the equation you use. So don't write this, but 4x plus, I'll put parentheses here. Everybody see I've copied the second equation, except I left a blank where the y is? Yes? Don't write this part in red. Instead of y, well, according to this thing in blue, y is equal to 5 minus 4x. So would you believe that I can replace that y with just 5 minus 4x, right? But then what happens when we clean this up a little bit? What happens to those 4x's? They cancel, and what do I get? 5 equals 5, which is undeniably true, but less than useless, right? So if you just use the same equation, you don't get anywhere. You don't get anything good. So plug into the other equation. Okay, so here we are plugging into the first equation, the one we didn't use just yet. I'm going to copy everything in that equation except for the y, which I'm going to leave a space. So it says 6x minus 2, and then instead of y, I'm going to leave a space. Put parentheses around that space. According to the first equation, we're just copying now, equals what? I'm not going to put that in just yet, but I'm just looking for the right-hand side here. It's the -3, right? All we're doing is copying that top equation, but just leave a blank space where that y is supposed to be. And then Zach had the right idea. In the blank space, the first equation we said it was a y. But what is y equal to according to this blue thing is 5 minus 4x. So what we are doing is substituting. Instead of the y, we are putting 5 minus 4x. It's a fairly straightforward process once you understand why it's allowed. So are there any questions about what we did there, that substituting step? Okay, so let's go through the algebra to solve this thing for x. It has only one variable now, that's good. So the first thing we need is to distribute that -2. So we get minus 10 minus 8x. Why is it plus? Is it plus or minus? Plus. Okay, so we distribute that -2. And then we'll smush our x's together. I count 14 of them. And then 2 more steps to solve for x. So add the 10, and then divide by 14. So always leave your answer as fractions, but always reduce those fractions. Yeah. Okay, so x equals 1/2. What do we still need to figure out? Is the value of y. Remember, we're looking for a point. It's got an x and a y. Okay, so here's the deal. You can take this x equals 1/2 and plug it into a number of different equations. Basically, any equation that you see in this problem that has both x and y in it, you can plug in. Any equation that has both x and y, you can plug in. So for example, I could plug into here because it has both x and y. I could plug into there, it's got both x and y. I could plug into either of these, but we didn't actually want to go that route. Or I could plug into here, and this is the one you want to plug into. Any of them is fine. But your goal here is to find the value of y. If you plug x equals 1/2 into this equation, it's like gift wrapped for us, right? It's going to be y equals, and then whatever the answer is, that's it, we're done. So go back into that equation and substitute the x equals 1/2. Okay, so I'm going to copy this thing right here. Y equals 5 minus 4 instead of x. What are we putting instead of x? 1/2. And then we just need to crunch the numbers. So half of 4 is 2. 5 minus 2 is 3. So x equals 1/2, y equals 3. Questions on that? Okay, so I have never typed up like an explicit step-by-step set of directions for the process that we just followed, because I'm interested in us really understanding what we're doing. And if we understand what we're doing, then it's a pretty natural process to follow. That said, if you're really a process-based person, then I'd encourage you at some point later today to try to write down step-by-step instructions. And if you get to the point where you can write down the step-by-step instructions, then you've probably internalized what this method is after. Okay, so there's one other technique we're going to talk about today. That's this thing called the elimination method or the linear combinations method. So we just did something called substitution, where we took the value of one variable and substituted it in to another equation. Here's the basic idea for this. Would you guys agree that if A is equal to B and C is equal to D, then I can add up the two equations and A plus C is definitely equal to B plus D? You guys buy that? Do we need to see an example? Anybody not convinced? Here, look. All right, so 2 times 4 is definitely 8, right? 5 is definitely equal to 1 and 4, yes? So if I add these two equations, what does it say? It says 2 times 4 plus 5, adding those things, is equal to 8 plus, and then add this guy, 1 plus 4. Is it true? Yeah, and they're both 13, right? All we did is add 8 and 5 in a couple of different ways. Okay, so if you have two equations that are true, then you are welcome to add the equations together, which gives you a brand new equation. All right, so that's what we're going to do here in number 7. Let's take a look at these two equations. 4x minus 5y equals 3, and 3x plus 5y equals 11. If we were going to use the technique from the previous page, we would have to first start by solving one of those equations for one letter. And remember, a lot of times that leads to fractions. Is there a nice way to avoid that? Can we avoid getting to fractions if we solve one equation for one letter? The answer is no. What made it so we could avoid fractions in the last problem? Was that there was a 1 in front of one of the letters. It was 1y. But here, there's not a 1 in front of any of these letters. So if you do the substitution technique, you're going to end up with fractions. There's nothing wrong with it, and you'll get the right answer as long as you do the process correctly. But there is another technique, and oftentimes if I can't avoid fractions with substitution, I will do this other technique. So here's the basic idea. We have two equations. If we add them up, we get a brand new equation that's valid, yes? Okay, let's add them up and see what happens. Add up these two equations. How many x's do we have when we add up? 7x plus, how many y's? Oh, 0 y's. That's quite fortunate. Equals, add up the right-hand side. 14. Everybody see the adding? And why is this equation better than either of the two we had before? It is put together. Yeah, there's only one variable here, right? It's just x. The other equations both had x and y. That's complicated. This equation just has one letter, x. Easy. 7x equals 14. X is 2. Victor. Yes. You could say minus 0 if you want. Ultimately, generally, you don't even write that at all. You just say the y's cancel and you just jump right to here. Yeah, but subtracting 0 is the same as adding 0, so it's fine to write it with a minus. Okay, So we got x equals 2, but we're not done. Also have to find y. Okay, remember I had said before, you got to plug into any equation with x and y. In the previous problems, there was a nice equation that just said y equals. That was the one we were after. We don't have that nice equation here. So there's actually a little bit of work involved in finding y. You're going to take the x equals 2, plug it into either equation. Personally, I'm jumping to the second equation because it avoids that subtraction symbol, and we as a species are just not as good at subtracting as we are at adding. So I'm going to grab the second equation. So here's what it says. 3 times x plus 5 times y equals 11. Notice the blank space where there used to be an x. And what did we discover is really the value of x? 2. So we just plug a 2 right there. And now you have some work to do to find y. So take a moment and do a little bit of algebra to find y. I got y equals 1. Is that right? Okay. So that's it. X equals 2, y equals 1. So all that made this thing work was that when we added these equations up, the y's disappeared. Well, that was rather lucky. So what if we have a case like down here, number 8? First of all, substitution is my go-to technique. I prefer that technique, and I actually think it heads somewhere better than this thing in general. Yeah, Brittany? Yeah. Yeah, so Brittany's headed in the right direction, so we're going to get there in a moment. If we go back to our substitution technique, is it possible to avoid fractions when you solve one equation for one letter? No, there's no just invisible 1 in front of any of these letters. Okay, if you just add these equations up, do we have that really nice thing that happened above where the y's just cancel? If you add them up, what do you get? 9x, negative 3y. Well, that's too bad. That equation isn't any better than the ones that we have here. So we have one additional step to employ here, and that's to make it so that we get that nice case where the variables cancel. So suppose that we were going to try to make it so that the y's canceled. At the moment, there's 2y and there's minus 5y. Now, Brittany gave us the big clue there. We know that we're allowed to take any equation, multiply both sides by any number we want, right? As long as we multiply both sides by the same number, that's okay. So what we're going to do is we're going to multiply the first equation, both sides, by some number, and then we'll multiply the second equation by some other number in such a way that the y's will cancel. So I'm going to put numbers up here, and this is what Brittany was getting at, and then we're going to see what makes it work if we can't see it just yet. I'm going to multiply the first equation by 5 and the second equation by 2. I think because one's already plus and one's minus, I think, yeah. So we're going to distribute here. But when we hit that 5 with the 2y, how many y's do we get? So upstairs it's 5 times 2y is 10y, right? And what about down below? 2 multiplied by that negative 5y? It's negative 10y. Those are going to cancel. And that's why we're multiplying by these specific numbers. So let's write the new equations. 5 times everything, 15x plus 10y equals, is that 90? And then the bottom equation, 2 times everything, 12x minus 10y is 18. And what really nice thing happens when we add these two modified equations together? Those y's cancel. We just get a 0 in front. So let's add these equations up. How many x's? 27. How many y's? 0. I'm not even going to write it. And then add the right-hand sides as well. 108. That goes in evenly, doesn't it? Is it 4? Okay, so that's x equals 4. And then I'm going to put just some instructions here for you to try later. Just going to say find y, because I want to do this same problem a different way. Okay, so first thing, why did I multiply by 5 and 2? Why did those two numbers lead to this fortunate result? Yeah, canceled the y's. How did I come up with the numbers 5 and 2 looking at those equations? Yeah, it's kind of like a least common denominator thing here. Imagine you had denominators. Look at the coefficients of the, I'm sorry, we might not know that word. Look at the numbers touching the y's. There's a 2 and there's a 5. So imagine you had two fractions. One of them had a 2, one of them had a 5. What's the lowest common denominator? It's 10. And so you multiply by whatever you need to make each of them 10. What do you need to multiply the 2 by to get it to be a 10? Is multiply by 5. That's what I did in the first equation. I multiplied by 5 to make the 10. What does that 5 need to get multiplied by? It's a 2. So I multiplied by 2. Okay, so turns out there's a slightly easier way to use this technique on this particular problem. I focused on getting rid of the y's. There's nothing special about the y's. We could just as well get rid of the x's. So looking at the x's instead, I see a 3 and a 6. Imagine those are both denominators in two fractions. What's the LCD? The 6, right? The LCD is 6. We can make them both turn into a 6. In fact, one of them is already a 6. So that first equation you don't need to do anything with. I'm going to copy both of them here. So the bottom equation is already 6x. That's fine. How do I turn the top equation into 6x? Multiply by 2. Yes? That's going to make a 6. But if it's a 6, then they're both 6x. And when you add up both of these 6x's, they don't cancel. So I really want one of them to be the other sign. So how about we multiply by -2? So let's distribute that -2. And then we're just going to add these two equations as they currently sit. What happens with the x's? They cancel. How many y's do we get? -9y. Add over here, being careful with the signs. -27. And then divide both sides by -9. And we get y equals 3. Questions on the technique? So we've seen two techniques today for solving the same kinds of problem. Substitution, where you solve one equation for one letter and then substitute it into the other equation, or this elimination idea, where you first manipulate the equations so that when you add them, one variable drops out. Tim? That's a great question. Both of these problems both of these techniques solve exactly the same kind of problem. So on the one hand, you might be wondering, well, why do we need two different techniques to solve the same kind of problem? Well, I think that sometimes the substitution method is far easier, and other times this elimination method is far easier. Now I want you to be able to do both techniques. So this is going to be one of the rare tests where I insist that you solve this problem using substitution and this problem using the elimination method. So I feel like I might force you into using one or the other. So I need you to know both. Okay. All right, so before we do group work, there's just one funny case that we need to talk about. Let's take a look at number 9 on the next page. What's that? Yes, go ahead. Yes. No, at the tail end of this problem, what you do is you take either of the original equations and you plug in x equals 4. And then you just solve for y. So it's not a matter of doing the entire process from scratch again. Yeah. Okay, let's take a look at number 9. First equation, y equals 2x plus 1. Second equation, y equals 2x plus 3. Zach. So you could multiply one of them by a negative, and you're thinking of this elimination method, and then stuff will go away. Absolutely. Before we solve, let's just think about the graphs. They both have a 2x. What does that mean about these two lines? They're parallel. Are they parallel and the same or parallel and different? They're different because the y-intercept for the first guy is 1 and for the second guy is 3. So these are two different parallel lines. So what can you say about the intersection? It doesn't exist. They never meet. So there is no solution to this. But suppose that we weren't thinking graphically and we didn't recognize that these are two parallel lines that never meet. Suppose that we're just going to go through one of our algebra processes to solve this thing, not realizing that there's something funny happening. So let's go ahead and substitute. Instead of this y, I'm going to put that 2x plus 1, right? Because it's the value of y. So here's what it says. Instead of the y on the left, we're putting 2x plus 1. And then equals 2x plus 3. So that's the substitution method. And if you try to clean it up and get those x's to be on one side, you see that they just cancel. You get 1 equals 3, which is quite a rare thing to see in a math class. So the fact that the x is canceled clue you into this being one of our special cases. And if you get a special case where you get an equation that is blatantly false, then that means we have no solutions. This is our indication that we had the two parallel lines that never touch each other and are different. So that's what number 10 says. Maybe we can go to, Morgan, did you read? You did, right? Did you read already? Zach, can you read number 10, please? Okay, so our conclusion when you get something ridiculous like 1 equals 3 is there's no solution. Let's take a look at the second one. The first one I could tell just looking at it, oh, wait a minute, these are just two parallel lines. But the second one is not obvious to me. I can't tell just by looking at that what the graph is going to be. So let's just go through our algebra process. We're going to substitute. Instead of this y right here, what are we going to put? 2x plus 1, right? Just put what y is equal to from the other equation. So I'm copying the second equation, 6x minus 3, and then a blank space equals -3. And as Zach says, that y is really 2x plus 1. Questions on getting to that step? All right, so that's our substitution. Let's distribute that -3. And now what happens? The 6x's cancel, and I'm left with -3 equals -3, which is another special case because the x has completely disappeared. But this special case gives us a true statement as opposed to the previous one, which gave us this nonsense about 1 equals 3. So the fact that this one right here gives us a statement that is true all the time means that we're again in one of those special cases. Usually two lines just intersect at a point. Occasionally you'll have two parallel lines that never touch each other. What was the other special case? They're both exactly the same line. And you actually have infinitely many solutions. Any point on either line is a solution. And that's what this means. So we can say infinitely many solutions. And so that idea is summarized in 12. Brittany, could you read 12, please? Okay, so those are our two special cases. You know you have one of the special cases if the x's all magically vanish. To decide which of the two special cases you're in, whether it's the no solutions or infinitely many solutions, you just have to decide whether you're looking at a statement that is obviously true, like -3 equals -3, or one that is patently false, like 1 equals 3. Okay? Two special cases. Normally that's not what happens. Normally you get 1 point of intersection. Okay, so we have about 25 minutes. I think that's enough time to do the 3 problems in the group activity. They start on the next page. They are about different kinds of fruits. And if you finish all 3 of these, you can start the homework, which is on the next page. It's in the packet.